So thank you. I hope you can hear me all. Thanks for the
Yes.
introduction and also for the possibility to talk during this session. So today I want to show you a little bit of the story I'm doing through my PhD or went through because I started working on this beautiful mountain. You can already see in the back. It has a, let me check. Now I can switch the slides. It has a nice big fracture in the middle. It's about 2,600 meters high on the border between Austria and Germany. And it's a quite spectacular case because we can see that this mountain is going to fail at any time soon. This is all carbonate rock. We have this unstable side on the one side and the more stable side the other side. We have this main crack, which is almost open 4 to 6 meters on the top. And we also have some more lateral cracks on the side. And in the beginning, we started working here. Of course, first we wanted to know, okay, how big is this thing? So I'm not sure how good the animation will be on the on, but we had this 3D model and we tried to check which of these blocks could fail. And then we identified all the unstable blocks, and I also wrote it here. So it's always possible that this mass is further disintegrating. And I think, or right now, we also think that these blocks number 5 and number 6 fail first. But also an enlargement is possible, which we also did last summer. So we detected in this mass down here, we detected some signs of movements in the laser scan. So we also included a scenario with these masses. That's in total, we have 200 to 600,000 cubic meters of rock that could potentially fail. The next, of course, we went there and we wanted to monitor the site. So we installed a real-time monitoring system. This is a view from the top. We have several crack meters, which are measuring on the lateral cracks. We have 2 laser distance gauges measuring the opening of the main crack. We have inclinometers that measure the tilt of the different blocks. And we also have a camera and a rain gauge. The data are transmitted every 10 minutes. So now I think we have some nice data since 3 or 4 years. And now we are somewhat ready to have an early warning system. But then, of course, the first question of everyone was and is still, when is it going to happen? Do you know that? And yeah, we started thinking about that and said, okay, we could say something if this mass is accelerating, but we cannot start thinking about it when it's going to be like this. So we have to have something ready in the drawer, which we can take out. So whenever we detect an acceleration, we need to have a model and so that we can estimate the time of the failure. And this is what I worked on recently with some colleagues. And I want to dive into this a little bit more. So in the existing theory is that most of the unstable mass movements, we can describe the displacement of those by a classical creep curve. So we have a primary creep phase, then a secondary creep phase where the velocity is more or less constant. And towards the failure, we have a more and more accelerating phase in the tertiary creep phase, where the velocity is accelerating more and more. And then classically, we smooth the displacement somehow because we cannot take just the raw measurements. And then from the point we call the onset of acceleration, so the point where the tertiary creep phase starts, we can calculate inverse velocity and then just extrapolate this trend towards the future. And then the point where we cross the abscissa is the point where the velocity becomes infinite. And this is the forecast time of the failure. This is good so far, but then also identified that often or sometimes we have some drawbacks with this. And the first one is that in the literature, this is often applied retrospectively. So after a failure has happened, people analyze how good they could have forecasted the time of the failure. But this doesn't, of course, help for my case where the failure didn't happen yet. Then the second is that the smoothing, so when I come from the raw data to the smooth data, is not often clear or not always clear, although it has a great effect on the forecasted time of the failure in the end. The third one is the onset of acceleration. So this point is sometimes put arbitrary, or we need a human expert to sit there and decide when the onset has happened. And the last one is that we are not always sure how good is my forecast. So I need kind of measure of my uncertainty of the forecast, because a stakeholder wants to know, okay, is it going to be in 3 days or 3 days plus minus 1 or 2 days? Yeah, so then look at the real-time situation. How is it in real life? We usually start measuring in the secondary creep phase. And then at the time of analysis, which is kind of now, we don't know if we are already in tertiary creep phase or if we're still in the secondary creep phase. And then in our approach with the analysis code, we use a two-time approach. And the first one is that we smooth the raw data based on different smoothing window lengths, and just take the last n observations of my data and then get my smooth displacement. And I iterate this analysis with every new data point I'm getting from my measurement system. Then in the next step, I'm detecting an onset of acceleration automatically based on some simple criteria. So I don't need the human expert here right now. Of course, I still need it, but if I have a lot of data, it might be easier like this. And then once I have the inverse velocity, the onset of acceleration detected, I calculate my forecast, but I do not calculate just one forecast, but I use multiple velocity windows. And from that, I get a variety of forecasts for my time of failure. So by this is able to operate in real time prospectively. We have a multiple smoothing approach that helps a little bit to reduce the subjectivity of my smoothing approach. Then I have the onset of acceleration detected automatically. I will just show a bit more detail in a second. And I can estimate the uncertainty of my forecast by the calculation of more than one forecast. So the algorithm works like this. I get new data, I remove some outliers, and then I smooth the raw displacement data, as I just showed, with multiple windows, and then I get my displacement. Next, I calculate my inverse velocity with multiple windows again. And I also calculate quantiles of this inverse velocity. So I get the 50% quantile and a 1% quantile of this. And then I have to decide, or the algorithm has to decide, is the onset of acceleration detected or not? If not, we just continue with the next data point. If yes, we have to calculate the time of the failure. And this decision is made based on 4 criteria. So the first one is that the displacement rate must increase of the last smoothing window. The second one is that the inverse velocity must decrease for all of the velocity windows. And then the 50% quantile decrease represents a long-term decrease, a long-term accelerating regime. And the last inverse velocity is smaller than the 1% quantile, just means that we have also short-term acceleration in the system. Once we have this, all of these conditions true for one smoothing window, we detect, okay, here is an onset of acceleration. Now I want to show you some real data results from real data sets. First, you see on the plot on the left the displacement. Second, you see the inverse velocity over multiple velocity windows. And then on the third plot, you see the detection criteria, if they are true or not, to detect the onset of acceleration. Then the hard piece of the forecast is the life expectancy plot. So on the x-axis, we have the time when we do the forecast. So the most recent forecast is always on the right side. And on the y-axis, we plot the life expectancy. So this is something like how much time do we have left until we expect the failure. This is easily updated with every data point. And here we also calculate the mean of all the windows, and also add this gray area, which is dependent on the range of the forecast, and gives us a failure window, which is something like how a failure window where it's probable that the failure will happen. So this gives you the width of this window gives us a measure of the uncertainty of the forecast itself. And then last on the right side, I plot the box plot of all the past forecast until now. So this helps to evaluate the influence of different window lengths, and also if the latest forecasts lie within the previous forecast, or for example, if we have a trend to later forecasted times. So now I again hope the animation works with the online version, but this is a time-lapse animation of real-time forecasts. We see displacement, we see the inverse velocity already going down a bit here, and then we see the detection criteria. And this is data from the Prionso rock slope failure, which happened in 2012. Then once all these criteria are true, we detect an onset of acceleration and calculate forecasts. And we can see that in the beginning, these forecasts are widespread and we are not very sure with the forecast. So this doesn't help much in the beginning, but then soon later, these forecasts converge and show towards the same time. And it shows like something like May 12 to May 13 forecasted time of failure. And if we wait a little bit further, we can see that this is the time where the first forecast would say, okay, now it's going to happen. And in the end, doesn't show now, but this is the time of the failure. And we can see that it's somewhat on the end of the failure window, but we're still within this failure window. And yeah, then of course we did not do this just for one data set, but I've collected all the data I could find. And this is the results of all that. I know it's pretty small and much, so I will just focus on the top row. So this is the results from 46 data sets from 14 sites. This is the more frequent data we could have. So here you see the error of the forecast at the time of the actual failure. So this is post-failure analysis we did just to evaluate how good our forecasts have been. And we can see that some of them are too early on the left side, some of them are too late on the right side. But in general, we are pretty close to the actual time of failure, and the failure windows are usually something like 24 hours. In the next part, it's aggregated even one step further. So all the forecasts from belonging to one side of different sensors are merged to one value. And then the mean forecast error gets even less because we're just close to the actual time of failure. On the right plot, we evaluated how good the forecasts are over the time. So this is 5 days before the actual time of failure, and then we go towards the actual time of failure. And we can see that the forecasts get better the closer we are to the actual time of failure, which is something nice, I think. And we also see that the spread of the forecasts are getting a little bit less. Some of them are too early, but most of them too late, forecast too late, but most of them are too early, which is also, I think, better than too late, because then we are on the safer side. So if you imagine you would make an evacuation or something, it's better to evacuate too early than too late. The last thing I want to show you here is that usually we think that if a mass movement is bigger, we have a longer tertiary creep phase and a longer acceleration time. And if it's very small, it might happen very fast. This is also something you could guess from this data, but it's not enough data yet to really show a statistic correlation of this. But I think this is also one point which is very important for this land-aware network. So we can really use more data. We need more data with a high quality, where we know the time of the failure, where we know the volume of the mass movement, and where we have good monitoring data and not just one data point per week or something like this. Good. Then to stay in time, I will sum this up. I've presented this prospective failure time forecasting model. It's able to operate in real time, respectively. We have a multiple smoothing approach to minimize the subjective smoothing decisions. We have an automatic onset of acceleration detection, which help if we have a lot of sensors or big data. And we can estimate the forecast uncertainty by this multiple forecast calculation. Interesting, this works pretty good with a varying type of failures. So we have in this data sets, we have rock slides, we have rock falls, we have some topplings. We also have one ice fall. We have mixtures of those. We have different monitoring methods, GNSS, radars, total stations, whatever, and also a variety of volumes. And the same thing works with all of the same code, which is, I think, because we just use the displacement, which is the result of all of this in the end. So we already take a phenomenological approach, which is quite a good thing. This thing is, we put in a paper, which is unfortunately still in review, but I think it will be out soon, and I'm happy for questions.